So here is another method for figuring out what optimal model complexity we need to use, okay? And this method would be called train and test or train and validate, or more specifically, sometimes it's called holdout cross-validation, okay? The idea is as follows, right? So the whole problem with overfitting is that you fit the model to some data, and then if you get some new data, the overfit model might not predict or explain or capture the new data very well. Okay. Um, so what you do is have that procedure incorporated in your data analysis framework, right? So if you have a bunch of data, we divide that into three pieces. One is called the training set, one is called the validation set, one is called the testing set. Somewhat confusingly, in some circles, the validation set is called the testing set, and the testing set is called the validation set. But we'll ignore that for a moment. We'll give the definitions, at least for the purposes of our class, below. Okay, so what's the training set? Training set is actually what you use to fit the polynomial or fit the model. Okay, so so you divide the whole data into three sets, and you use the training set to fit, in this case, polynomials of various degrees n equals 1, 2, 3, etc. I should probably use a small m. Capital N is reserved for the data set size, I guess. Okay, and then you evaluate the mean square error for each of these polynomial fits. And then, as we saw, the training error, this is called now the training error, which is the mean square error for the training data set, the data set to which you're actually fitting the data. The training error will keep going down. This is intuitive, right? So you're fitting to the data set, and the more complicated the function that you're trying to fit to the data, the lower your error might be, okay? Now, I do want to mention that the fact that it keeps decreasing, or at least doesn't increase, has to do with the fact that an nth degree polynomial is a general version of an n minus 1th degree polynomial, right? So if you take an nth degree polynomial and then set the nth order term, nth degree term to 0, you essentially get an n minus 1th degree polynomial, right? So what that means is that anything an n minus 1 degree polynomial can do, an nth degree polynomial can do, and then potentially much more, right? So that's why when you increase the model complexity, the training error can either remain the same or decrease, right? It cannot increase by definition, right? And this is because polynomials form what's called a set of nested models, right? So there's the linear polynomial, quadratic, cubic, and so on. And the next model contains the previous model as a subset. And that's why things always improve, or at least at worst remain the same, right? Okay, so what do you do after training the data set, training the models on this training set? You get the best fit model for each of this model complexity. And then when you actually want to test the data, how good the model is, you actually use the validation data set, right? So recall, you divided the data into three pieces. You find the coefficients using this data set, and then find now the mean square error on this data set. And what will happen is that the validation error, mean square error, will kind of look like this, okay? So the reason why we are testing it on a different data set is that hopefully this different data set will have different noise/errors compared to the original data set, which means that if you fit to the noise on the original data set, you will do poorly on this new data set, right? But if you did not fit to the noise and sort of used a relatively nice model that tracks the model but not the noise, then maybe it'll do pretty well on the validation data set, right? So here's the idea. As the training error decreases, in other words, as the model gets better, the validation error will also decrease. And then at some point, the validation error, in other words, the mean square error on the validation data set will start increasing, even though the mean square error on the training set keeps decreasing. And this is the point. This is the point where what you're doing with the training set is you're actually starting to track the noise in the data as opposed to the general trends, right? So because you're tracking the noise in the training set, and because the validation set has different noise properties, even though you're doing a good job on the training set, you're doing a bad job on the validation set, right? So this is the ideal kind of curve. And what you want to do is to pick, say, the model complexity, in this case, the polynomial degree that minimizes the validation error, mean square error, rather than the training error mean square error. Training error mean square error, training set mean square error will just go to zero eventually, but the validation set mean square error will go down and then go back up, and you want to make sure that you will pick the optimal n for that. Okay, so that's the idea. There is an optimal value of n that minimizes the validation error. So what's the third set for? Recall that we use three different sets. Use the training set to actually fit models of different complexity, validation set to actually test how the mean square error goes down and then up, and then you pick the optimal value of n that minimizes the validation error. And then the testing set is kind of a test of your optimal value for the model complexity, right? So the training set you've already used to actually fit the data. The validation set you're also using to actually pick the optimal value of n. And then the testing set is kind of a third set which you have not yet used in fitting your function. And use the testing set to actually report something like, okay, if you got a completely new data set that you've not at all used in either getting the coefficients or the optimal model complexity, your error on the testing set is kind of a representative error on potentially new data that you've not seen before at all, that you've not used to build the model, right? So that's why we divide this into three sets. Very often people might just do training and validation and not do testing. And that's common, and it's, I guess, fine in some situations. Okay, so that's how you do train, validation, and test. We'll see a MATLAB version of this in a minute. Now, if you do, like I said, this version is called holdout cross validation. Because you're holding out some part of the data, not using it, and then you're validating your model using that holdout data. Okay. So the problem, though, is that if you break up the data into these three pieces, and you break it up sort of in a random fashion, it's not like the first so many data points or training set and so on. You just break it up randomly. Depending on how you break it up randomly and how many, what percentage you allocate to training, validation versus testing, right? So usually people might do 60% training, 20% validation, 20% testing, or 80% for training, 10% and 10% for validation and testing. It really depends on how much data you have. If you have a lot of data, this might be sufficient. If you don't have that much data, maybe you want to do this, or vice versa, depends on the details. In any case, if you randomly split the data set into these three pieces, depending on the random split, you might get the validation error to look different, right? So it's never this clean that there is an optimal validation error. You might, for one split of the data, you might get some curve that looks like this. For another split, you might get some other curve that looks like this. For a different split, you might get a different curve. So what what do you want to do? And each of these actually might have slightly different optimal values of n. If you have a large enough data set, this might not matter all that much. Um, but one way to account for this randomness of the split between the three data sets is to actually do this multiple times. So basically do the validation set, training set, split multiple times and draw a curve for the validation set mean square error that is basically a mean of all these curves, all these different splits. So that's one way to do it. Another way is called what's called k-fold cross validation. It's not necessarily a better idea, but it's a good idea, and that this is perhaps the most common in the machine learning literature. What's called k-fold cross validation, and I'll discuss this in the next short video.